Today we are walking through the paper titled Self-Distilled RLVR.
Can we start with the big picture of what this paper is trying to solve?
The paper asks how to keep the fine-grained guidance of self-distillation without inheriting the instability and leakage that appear when the teacher sees privileged information. Its answer is RLSD, short for RLVR with self-distillation.
Why were the earlier training options not enough?
Regular on-policy distillation, OPD, can speed learning, but it needs a stronger external teacher and usually the same vocabulary on both sides. On-policy self-distillation, OPSD, removes the separate teacher, but the privileged teacher sees reference answers or verifier signals that the student never gets at test time.
So the problem is not only cost?
Exactly. The teacher is conditioned on extra information the student is not, and distribution matching under that asymmetry is still posed. The paper argues that this leaves an irreducible gap, then shows it to stage pattern, early gains, followed by leakage and degradation as the model learns shortcuts from the input to hidden hints instead of better reasoning. That is the setup for LSD.
What does our LSD change in the actual update rule?
It stops using the privileged teacher as the target distribution. Instead, the verifier reward still decides whether a trajectory should be reinforced or penalized. And the teacher only tells the optimizer which tokens deserve more or less weight inside that trajectory. Now let us put the main method figure on screen.
Where is the key split in this diagram?
The important split is between direction and magnitude. The student trajectory is still judged by the environment reward, but the same model is also run with privileged context to measure how much each token was helped by that extra information. That measurement becomes a weight, not a target to imitate. The first key equation defines that token level signal.
What should I read from delta t before the algebra?
Write delta t as privileged information gain. It compares how likely the chosen token looks to the student alone versus to the teacher that also sees the hidden signal. If that gap is large and positive, the extra information strongly supports the token. If it is negative, the extra information pushes against it. Then the paper turns that signal into the clip token advantage used for learning.
How does this avoid leakage instead of recreating it in a different form?
Because the sign still comes from the sequence reward A, not from the privileged teacher. The teacher can only stretch or shrink credit within a bounded range. So it cannot flip a bad trajectory into a good one or steer the gradient toward hidden answer tokens. That is the structural reason the paper claims our LSD stays leakage-free while still getting dense token credit. Next, let us look at the main performance figure.
What is the strongest result on this chart?
On the Q13VL 8B instruct runs, our LSD climbs faster than GRPO, avoids the late collapse of OPSD, and reaches a higher ceiling. The figure also makes the speed claim concrete. Our LSD at 200 steps already beats GRPO trained for 400 steps. Now let us bring up the diagnostic figure behind the failure analysis.
How does this figure support the theory instead of just showing one bad one?
Because all three pieces move together. Leakage counts rise over 100 steps. Validation accuracy peaks around the first 10 to 20 steps and then drops. And the on-policy KL under OPSD stops shrinking, while OPD keeps converging. That is exactly the behavior you would expect if the student reaches the best marginal match it can, then keeps absorbing harmful shortcut signals it cannot legitimately represent. The next figure shows what happens over the longer training run.
What extra story do these training dynamics have?
They show why our LSD is not only better at the end. It rises more steeply early on, keeps higher entropy than GRPO instead of collapsing the distribution too aggressively, and the clip ratio stays around 3 to 6%. Which means the teacher signal is active but bounded like a trust region.
Do the benchmark averages tell the same story?
Yes. Across 5 multimodem reasoning benchmarks, our LSD reaches 56.18 average accuracy at Fukai and 50 to 0.78 at Decay. That is for 0.69 points above the base model and 2.32 above GRPO on average in the 4K setting, with especially clear gains on Math Vista and Math Vision.
What is the practical takeaway for someone already using verifier-based reinforcement learning?
The paper treats our LSD as a drop-in replacement for GRPO's uniform advantage. The added cost is one extra forward pass to get teacher logits. And the payoff is denser token credit without letting hidden information decide the learning direction.
So self-distillation is useful here only when it scores token importance, not when it dictates the target distribution.
That is the paper's core claim. Use privileged information to scale token credit. Keep correctness anchored to the environment reward. And you get faster and more stable reasoning training without the collapse that hurts OPSD. That wraps up this paper walkthrough.